Okay, good afternoon, everyone. Today, what we are going to do, as I sent you in your email, that I will take up questions concerning determinant. And then once we're done with that, I will go back and pick up on section 2.8 to 2.9. I made a point to let Professor Tarfolaya teach you determinant because it's slightly independent from the other topics. So I can now answer questions about determinant, and then I'll go back and pick up subspaces and basis of a subspace. Okay. So do you guys have any questions about the homework? First, about determinant. I'm going to review it. Not review it. I'm going to do some problems myself, but if you guys have any questions, I would appreciate them. Okay. So the part of determinant that very important for us in linear algebra, besides knowing how to actually compute it, that I know Professor Tarfolaya gave you a lot of examples, is that the relationship between determinant and the invertibility of a matrix. And that's the part I am going to review one more time. So let A be a n by n matrix. So it's a square matrix, okay? Then, sorry, okay. Then, and let us A be, I'm going to emphasize its column, A1, A2, and AN. Then a matrix A is invertible. It means we can find something to multiply it by to give me the identity in terms of determinant if and only if the determinant of A is different from 0. Absolutely important result. So a non-zero determinant, so if you have a matrix and you evaluate the determinant and you get a non-zero number, then this is give us a criteria for the invertibility. Now we've seen other criteria of the invertibilities, which are easier to check than the determinant. But the determinant is one more criteria that tells me that a matrix is invertible if and only if its determinant is different from 0. And let us see what's the consequences of that. So some of the consequences of that. Okay. And here I'm going to invoke, get back into the picture, the invertible matrix theorem. And that's AN. Suppose this is my matrix A. Then there is something we talk about called the followings are equivalent. It means if one is true, the others are true as well. The following are equivalent. Means one of the statement is correct, every other one is correct. And this tells me the following. Suppose I'm going to invoke the determinant. So I'm going to add this idea. So suppose the determinant of A is non-zero. So I have a matrix. You know, I plug it into a calculator if you want. I compute the determinant. I find a non-zero number. Then what can we say about the matrix? First, it means it is invertible. Remember me that I can find the thing, I multiply it by to give me the identity. Not every matrix has these properties. Then the columns of A are, it's invertible, it means the columns are linearly independent. So if you have a matrix and somehow you know that the determinant is not 0, you can immediately conclude that the columns are linearly independent and vice versa. If the columns are linearly independent, as long as it's n by n matrix, then the determinant is different from 0. Another thing we can say that the system, and that will play an important role for us in the last section of this book. the system AX equal to 0. So a non-zero determinant guarantee that the system AX equal to 0 has a unique solution, namely X equal to 0. Okay. So a non-zero determinant tells me that the matrix in question is invertible, columns linearly independent, the system X equal to 0 has a unique solution, and there are other things, of course, that because of the invertibility, then if I take the span, it means all the possible linear combination of the column. So if I take the span, I get every vector in Rn. And because of the invertibility, it means A should be row reduced to the identity. But the main new idea here is that a non-zero determinant guarantee invertibility, linear independent vector, uniqueness of the solution, the span Rn, and the row equivalent to the identity. Okay. Now, with this in mind, I would like to do some problems from the book, basically to emphasize this idea before I proceed, unless you guys have specific questions, because I did give you homework and I emailed you about it. So let me look at number 21 in the book to emphasize what I've been talking about. So it's 21, section 3.2. Okay, it tells me the following. They have a matrix A, 2, 1, 3, 6, 3, 9, 0, 2, 2. That's my matrix A. And the question is, use determinant. Okay. Use 2.8 has to wait till after I finish determinant, then I go back to the previous sections. So the idea is that use determinant to check if A is invertible. Okay. Now, if they didn't tell us use determinant, we don't have to. If I want to check that the matrix is invertible without the idea of determinant, I ask myself, does it row reduce to the identity, which is a lot of time faster. So if it reduces to the row identity, it is invertible. Now, if they want us to use the determinant idea, which is sometimes also, especially 3 by 3 is not hard, then I compute the determinant and I make sure it is non-zero. So now I compute the determinant of A, which is 2, 6, 0, 1, 3, 2, 3, 9, 2. So there are a lot of ways to compute the determinant. As you guys should know by now, we go to the row or column that have a lot of zeros. Now, in this simple problem, this has a lot of have the zero. So I'm going to use the first row, cofactor across the first row. Okay, so what does this mean? So basically, we use the checkerboard sign. So it's going to be equal 2 times 3, 9, 2, 2 minus 6 times 1, 3, 2, 2. Okay, and now it's just a matter of computing this determinant and figuring it out. That I will get is 6 minus 18, 2 minus 6. And finally, the only thing I care about is it 0 or not. Then 6 minus 18, that's going to give me minus 12, minus 6 times 2 minus 6 minus 4. So that will give me minus 24 minus plus 24 equal to 0. What can we conclude immediately? Determinant of A equal to 0. What can we conclude about the matrix A? Invertible or not invertible? Because that's what the question is. So absolutely A not invertible. Okay, so that's how that's the idea of determinant. Now, a simple question to you now. Suppose I take this matrix and I row reduce it.
We don't see it.
Oh, do you?
Yes, now.
Yeah, reduce. What do you think is going to happen? I'm not going to reduce it. But what do you think will happen when I reduce it? It's definitely not the identity. We will not get the identity. So when I reduce it, I don't know exactly what it's going to be, but I am sure it's not going to be the identity. It means I'm going to have something like that. So you guys try it. I don't know exactly what, but it's going to be that. That's how we're going to reduce it. We will not have the identity. It means we will not have 3 pivots. So if you reduce this matrix, you will not have a 3 pivot because that's not invertible. And what else can we say? Those columns are linearly dependent. You try it, of course, because when we're going to solve here, I'm going to have infinitely many solutions. So that's the lack of invertibility. Okay. All right, I will do one more problem just as a review of those ideas and the review of the determinant as well. So I will look at number 26, for example, in the same section. And I have a matrix, I have columns, and the question is, I'll use the idea of determinant to decide whether the columns are dependent or independent. And my columns are 3, 6, 3, 5, sorry, -6 and 4. 2, -6, 0, 7, and -2, -1, 3, 0, 0, 0, 0, -2. Okay, so these are the columns. And the question used the idea of determinant, because that's the idea we're practicing, to check whether the columns are dependent or independent. Now, if they don't ask you use determinant, again, you go to the echelon form and you ask yourself, okay, what's going to happen? Are we going to have free variable or not? If they wanted to use the determinant as a practice, we're going to go after the determinant. So let me check back. 3, 5, -6, 4, 2, -6, 0, 7, -2, -1, 3, 0, 0, 0, 0, -2. Very good. So we're going to compute the determinant. Okay. Now, how would you compute the determinant of this matrix? That's my matrix A, and these are my columns. Okay. 3. All right, I'm rewriting it. So you guys tell me, how would you compute the determinant of this matrix? We go after the column with the most zeros. The column with the most zeros is this column. So we're going to do cofactor down the 4th column. Otherwise, it will be nightmare. If I use the first row, it will be really hard. So that's why we do cofactor down the 4th column. So let's see how we do the factor. We start with the checkerboard sign, plus, minus, plus, minus, and a plus. So what's the cofactor? It's 0 times, it's a 0, plus is 0, that's a 0, minus is 0, it's a 0, so I only have one determinant. So that's -2 times the following. Scratch this, scratch that, it leaves me with this 3 by 3 determinant. -1 and 3. Okay. Now at this stage, I can compute this one also using cofactor, because I have a 0 in here. I can use cofactor down across the 3rd row or I can use cofactor down the second column. So this would be equal to minus 2 times. So I'm going to use cofactor across the third row. Okay, so I go after the zeros. So this will give me, that's a plus, minus, plus, minus, a plus. So this is the one I'm going after. So it's minus 6 times what's left. And then it's a 0, and that's a plus 3 times what's left, which is 3, 5, 2, minus 6. Okay. And now I compute this. Let me see if I do it quickly as much as I can. Minus 2, and that's going to give me minus 12, I think, plus 3 times minus 18, and minus 10. Please make sure. So finally, I will get minus 2 times minus 6 times 14, plus 3 times, give and take, a stupid mistake I did. And this will give me how much? So it's give me minus 2. So I only care whether it's a 0 or not. So granting I'm not doing any stupid mistake, I will have 4 times is 6, which is minus 84. And no, that's minus, that's a plus. Minus 3 times 28, that's give me 84. That's giving me a 0, which again tells me that my matrix, my column vector, so this means the column vector, the columns are linearly dependent. Because the determinant is 0, it means the columns of the matrix are linearly dependent. Okay, so now if I take this matrix and I row reduce it, I will not get the identity. If I solve the system AX equal to 0, I will have infinitely many solutions. So automatically a lot of things will happen from this number that we call the determinant. Okay. All right. What are the properties? I mean, there are other properties of the determinant that I really urge you to do the homework. I honestly urge you to do them so you can learn them. Okay. All right. I'll finish with one problem and then I will assign those again for you for next time. One problem that emphasizes a little bit the property of the determinant. So I will look at number 39 just to remind you the properties. And here I have two matrices, A and B. The determinant of A is minus 3, and the determinant of B is a 4. And the question is, find the following. The determinant of A times B. The determinant of 5A, and sorry, A, B are 3 by 3. And then the determinant of A inverse and the determinant of A to the power 3. All right, you can do them one by one. And as we do them, remind you the property of the determinant. So if you multiply two matrices, what happened to the determinant of the product quickly? I'm sure that Professor Tarfolea talked about that. What's the determinant of the product? Determinant of A times the determinant of B. Okay, so very useful property of determinant that if you have the product of two matrices, determinant of A times B is determinant of A times the determinant of B. The determinant of A is minus 3. The determinant of B is a 4 minus 12. Okay, 2. When you take a matrix, you multiply it by a scalar. It means you multiply every term of the matrix by a scalar. So you have a whole new matrix where every term is multiplied by 5. So you create a new matrix. What's the determinant of the new matrix? So what is the property here? Let us remember. What's the property? Suppose A is a n by n matrix. That's the rule in general. Then if I take A, I multiply it by a constant. Okay, constant. Then I create a whole new matrix. And the determinant of the new matrix is K to the power, the size of the matrix, times the determinant of A. That's how it works. It's not K times the determinant. It's K to the power, the size of the matrix. So this is going to be equal to 5 times. And B are 3 by 3 matrices. It's 5 to the power 3, the determinant of A. It means 5 to the power 3 times the determinant of A, which is minus 3. Okay. Now, what's the determinant of A inverse? Okay, the properties of that. We have a matrix, it has an inverse. And the determinant of A inverse, that's a new matrix. If A inverse exists, it means the determinant of A is non-zero. So that's 1 over the determinant of A. So be careful, that's a number, not a matrix here. The determinant of A inverse is 1 over the determinant of A. The determinant of A is minus 3. Okay, so that's a quick review of the property of determinant. Finally, what's the determinant of A to the power 3? But what's A to the power 3? It's A times A times A. So this will be, since it's a product, I can multiply determinant, which is going to give me 3. Determinant of A is minus 3 given in the problem. So that's minus 3 to the power 3, which is minus 27. Okay. And this will give you a quick review of determinant. Please finish the problems that I didn't do to help you know those very well. Okay. All right. Now, I will go back to subspaces and basis of a subspace. First, I have to review, of course, with you a little bit the definition of a subspace and then the null space and so on. So let us a little bit. So back to section 2.8, 2.9. Okay. So first, let me review what's a subspace and I will work out some problem. So let's see definition. You guys have that with you, so I don't need to repeat it. So let H be collection of vectors in Rn. We say that H is closed under vector addition if whenever 2 vectors are in it, their sum is in H. It's closed under scalar multiplication. If whenever a vector x is in H, multiplying it by a scalar, the new vector will also be in H. And we say that H is a subspace if 0 is in H is closed under vector addition. It means whenever you add 2 vectors, when in H, their sum is in it, H closed under scalar multiplication. So that's it. So there are collections of vectors in R2 or R3, in R4, they have very specific properties, which are the 3 properties. And in last time we met, I told you that the subspaces of R2 are lines through the origin, all of R2 and 0. The subspaces of R3 are line through the origin, plane through the origin, 0, and R3 itself. So that's to give us an idea. All right, today we're going to do one of the worksheet I put on Blackboard and to give you some kind of flexibility to how to show that it is a subspace. So I will write the problem and we spend a few minutes on each one of them to figure out whether it's a subspace or not. So my first example, this was on bright space, is let H be all vectors x1, x2 such that x1 plus x2 equal to 1. So that's the worksheet that you have. And the question is it a subspace? If so, show algebraically that it's a subspace by showing that it contains 0, close enter addition, multiplication. If not, explain why it's not a subspace. So we're going to take up those problems as fast as possible. So problem number 1. Is this a subspace? It means does it satisfy the criteria of a subspace? So I'm looking at all the vectors. That's that the sum of their component is 1. Okay, is this a subspace? Yes or not? What do you think? Remember the criteria. You have to memorize the criteria. So what's the first criteria of subspace? First criteria, 0 has to be in it. Second and third. So in this one, is 0 is in H. Absolutely not. Why? Because the 0 vector is 0, 0. And H is every satisfy, and 0 plus 0, of course, equal to 0, which is different from 1. 0, not in H, means H not a subspace. Done was the first one. So the first thing we ask ourselves, is it subspace? And geometrically, x1 plus x2 equal to 1 are all the points which are on a line that doesn't go through the origin. But it's not easy always to know the geometry. That's why we do those problems algebraically. Okay, B. Again, I'll tell you what B is, and I want you to think with me to figure it out. So B. H is all the vector x1, x2, such that x1 bigger or equal to x2. So example of vector in H, everything where the first component is larger, like 3, 1, 4, 1, I don't know, 5, 0. So these are example of vector. The first is larger than the second. So the question is a subspace. We go through the list. Is 0 in H? Yes, no, quick. Okay. Yes, no, quick. I want answer on chat. Yes, because what's 0? Is the vector 0, 0? Of course, is satisfied. So 0 is in H. Okay, that was. Now, this doesn't tell me much. Now, is it closed under addition and scalar multiplication? Usually, I like to start with scalar because it's easy to check. And if it fails, I'm done. If it doesn't, I move on. So the question now is H closed under scalar multiplication? Okay, let us think about that. What does it mean? It means if I take a vector in here, where the first component is larger. So let us a little bit, if you want, I'm going to do scratch here. I'm going to really try to think about that. If I take a vector in H, okay, what does it mean? It means the first component is bigger than the second. And I scale it. So I'm creating a whole new vector. Okay, that's a whole new vector. And the question is, this new vector that I created, does it satisfy this condition? So I'm really thinking before I do the problem. So if the first one satisfies the first component larger, will the second also satisfy this condition? What do you think? Necessarily. Okay, it's not, because a negative scalar will make less negative. Okay, so one of your classmates told me no, because if x1 bigger than x2 and you multiply by a negative scalar, you're gonna make the first component less than that. It makes sense. So now, is H closed under scalar multiplication? After you analyze your problem, what are you supposed to give me? And no, but no will never satisfy. You have to give me an example. No, because let me take X to be the vector, for example, 5, 1. X is in H because the first component is larger than the second. However, if I scale it, suppose I take C equal to -1, and I take C times X, so I'm creating a whole new vector. Okay. Then this is not in H because -5 is less than -1. Okay, so you have a vector in H, 5, 1. It is in, but scaling it will take me outside it. So that's not a subspace. So I don't have to check addition anymore. I'm done because it's not closed. So H, not a subspace. Okay. I'll do one more. So to give you a feeling. So let me take C. So this way I can move on basically strong footing. Okay. And then I will review the null space, and next time I will move forward. So H are all the x1, x2, x3, such that equal to 0. And my question is this a subspace? All right. First is 0 in H. Okay, 0 means 0, 0, 0. If I add 0 plus 2 times 0, this is equal to 0. So yes. 2. As I said, I like scalar multiplication because it's easier to deal with it. Now, is H closed under scalar multiplication? Okay, all right, let's see. Suppose I take a vector in H. In H means when I add those components, I should have a 0 vector. So there are very specific ones. Not everything is in H. Now, if I scale this vector, I get a whole new one because it has different components. And the question is this new vector in H? It means does this new vector satisfy this condition? So if the x1, x2, x3 satisfy this equal to 0, will this new one satisfy it? So I look at them. I say, okay, if I take that and I take away this, I know that without the C's, I get a 0. So I said, if I factor out the C's, but I know that this is in H. I know that this is 0 because the original one had this property. Now my question is when I scale it, does it have? So this is equal to 0. Therefore, this is equal to 0. So it's closed under scalar multiplication. And finally, under vector addition. Okay. So here, I'm starting with x1, x2, x3, 2 vector in H. And my question is, so that's in H and that's in H. So in H means the components are very particular. They satisfy this condition. And here, the component also satisfy this condition. So now I'm going to take their sum. And this will create a whole new vector. And my question is, this new vector I am creating satisfy this condition? All right, so I ask myself, okay, let me take, so I take that plus that's the condition. And I ask myself, is this satisfied for this new vector? And I think I did something along those lines before, but this is a quick review of everything. Okay, does it satisfy? I know that this is 0. I know that this is 0. So this new combination, is it 0? And the idea is that, yes, it is. You can start rearranging. So rearrange. I will get x1. I plug in the 2x2 here, minus 3x3. And I add to it the y1 plus 2y2 minus 3y3. Now, this x is in H. It means it satisfies this condition. This one in H satisfies this condition equal to 0. Therefore, it is a subspace. All right, so this C is a subspace. That's D is a subspace. C, you guys will have to do it by yourself. So this means geometrically, for those who remember 261, that's a plane in R3 through the origin. And it's definitely a subspace. Okay. Now there are, to every matrix, we associated a subspace called the null space. And one of your classmates has a question about that, if my memory is right. No, it's something else. So we associated to every matrix, we associate the following subspace. So the null space. Okay. And what is the null space? So we have A, n by n matrix. And the null of A is all the solution. So the null, all solution of the system AX equal to 0. Okay, so the null, all the solution. It means X in the null of A means X is a solution of AX equal to 0. That's what it is. Now, what we proved last time, so first an example, quick example to understand the null, and then a remark about it. So let me take an example. I think I did that before. Suppose I take A to be the following matrix. Three, 3. And the question is, find a non-zero vector in the null. What does it mean? X in the null means AX equal to 0. Find a non-zero vector in the null means find a vector X, a non-zero vector, such that AX equal to 0. So find a vector in the null is really basically means solving the system AX equal to 0, because the null are all the solution. The system has a lot of solution. The null is all the possible solution. So here the idea is that we take A, 0, we solve, and we reduce. If you reduce it, you get this one. Zero, 0. Now I solve. Those are my basic variable. And x3 is free, so it's going to give me x3 free. We set this to be my parameter t. x2, it's going to be minus 3t. And x1, 3t. It means every solution in vector form, they have to be in vector form, is of the form 3 minus 3, 1. So a non-zero vector in the null is, you can take 3 minus 3, 1. Okay, so that's what the null, all the solution. Now what's special about the null is it's a subspace. So the null is a subspace. It means it has a theorem, and I proved this last time, I will not prove it. So suppose a m by n matrix, then the null of A is a subspace, meaning that if two vectors are in the null, it means you have two vector solution of x equal to 0, their sum is a solution. It's a subspace of R what? R what? What should I put here? Think with me a little bit to figure it out. What should be R? So to figure it out, what's the null? The null are those x's that make ax equal to 0. That's the null. They are the solution. So if A is m by n, x has to be n by 1. So that should be n. So it's important to know where your vectors are. So it's a subspace of Rn, which means that if I give you two solutions of the homogeneous system, x equal to 0, their sum is also a solution. That's what it means, what is subspace. If I give you a solution and if I scale it, then C times the solution will also be a solution of the homogeneous system. And if I remember last time, I asked you the following question. I asked you to a little bit interact with the idea of a subspace. I told you, so suppose I take a matrix A, and this is my matrix, 2, 4, 6. That's a matrix. You don't have to worry about it too. That's a matrix A. And I told you that the vector U and the vector V are in the null. Okay, what does it mean to you? What does it mean to you? What does it mean to you? If I tell you those are in the null, I'm telling you that it means to you, it means if I take A, multiply it by U, I should get a 0. That's what it means to you. If I take A times V, I get 0 because the null are all the solution. If I tell you those in the null, it means I'm telling you those are the solution. So now I ask you find, I give you 2, find 4 other vectors in the null. Just to elaborate a little bit on the subspace. If I give you 2 vectors, can you give me another one? The null is a subspace means whenever a vector is in the null, scaling it will be another vector in the null. It means another solution. Adding 2 vectors in the null, you create another vector which is in the null. It means you create another solution of the system. So if I tell you find 4 other vectors in the null, can you give me that? A lot. U plus V. This vector will satisfy, this vector is a solution. That's what we're talking about. It's a solution. 2U plus V. That's another solution, and so on and so forth. Minus 2U, any linear combination is a solution. That's really what it means to be a subspace. Okay. All right. With this in mind, I think I'm hoping to get you back to where we were. I did a review for determinant and I did a review for subspaces. Next time, of course, we're going to move on. Your homework for next time will be exactly what I assigned for today. So you guys can go over it. And next time I will do the basis for the subspace and we'll finalize 2.9. Now, part 2 is I need to talk about exam 2, which is of course being postponed. I have one idea in mind, but I have definitely to make sure all of you will agree with it. My idea is, because I don't have a lot of time, I lost time in this class and up in all my classes. So my idea is your exam will be next Monday. Okay, so exam will be next Monday. But listen to me carefully, which is my memory. I forgot what's the date. I thought I remembered. Monday, it will be the 23rd. Okay, my idea is the following. The class will meet as usual. So class will meet where I can answer all your questions about the review that I'm going to put on Brightspace today. So the class meet as usual. So I won't need extra hour for the review. And my plan is to open the exam like at 4 p.m. that day and close the exam at 9 p.m. So you guys can do it on your own. The exam will not require 5 hours by any stretch of the imagination, but that's for you to be flexible. Now, that's my plan, but I want that all of you tell me, yes, you can do it. So any student has any objection, I will email again the info to see. Any student has any objection about that? Okay, anybody else beside your classmate? Please, you have to do the objection now.
There are some in the group chat.
Yeah, I'm reading them. Oh, okay. All right, so a lot of students have to go to work. Thank you for the arrangement that I record. Weekend, I don't really like weekend because I would like to review with you on Monday. Okay. Okay, I'll think about it tonight and I will email all of you again and see if you have objection. So, okay, Tuesday, or no, Wednesday is a day off, Nina. I can't. 24 hours is an exam that should need 1 hour. 24 hours is pushing it. Tuesday, is anybody open on Tuesday? Do you guys have problems on Tuesday? Who has issues on Tuesday? Work all day, what time? The same time frame. Oh, no. Oh, wow. Okay. All right, I was hoping this would work. Unfortunately, it didn't. Sorry. Okay, I'll think about it tonight and I will, guys, let you know this evening. Okay. Yeah, no, I want everybody to be really, I understand. All day Monday is bad for me. Okay, all right, I will think about that. Be ready for the exam next week. I'm gonna put the review for you tonight and I will think about what fit all the class. All right, so let me, okay, I'm getting a lot of messages. Okay, I will try to accommodate as I will try to see what to do tonight. Okay, in the worst case scenario, I will run the exam during the class time. If what about during class time? This will take away the review from you. Okay, I will email you tonight. I'll think about it myself. I will email you tonight and tell you what my decision is. Is that clear? So expect an email from me tonight, and I will tell you what's the decision.
I have a question.
Yes.
Can we do, for example, class time and extend like 2 hours from it? So
Yeah,
everybody,
I can do that. The only thing that you guys will not have a review. It's fine with me.
so it's not gonna be 4 hours or 5 hours, just class time.
I will have to have class time, but I'll have to of course give you a bigger window. So it could be class time. Okay, so it seems that that's the fairest. So the class open at you guys at 2. Okay, and
Maybe to 5, 6.
or actually, let me do that. I'll open it at 1:30 all the way to 5. What about this time? This will be very much within our time. The exam should take 1 hour. So if I open at 1:30, you guys should be done basically by 3 o'clock. Why not open it at the start of the class? But then I cannot do that. I want to be fair to everybody. Okay, this is
The best option.
okay. Anybody has any issue with that scenario? Then this will be during class time. So that's your time. Anybody had any issue with that scenario?
I have a question.
Please
I
talk.
like that, but maybe could you like, you know how you record your lectures and then you post them on your YouTube?
Yes.
Maybe could you just record yourself going through the review so that way we could watch that whenever it works for us before Monday?
Oh.
So
I mean,
that way
I'm
we-
gonna, okay, I'll think about that. That's not a bad idea. Okay, I'll think about that. But then next time will be a regular hour. Let's get that very clear. So Wednesday will be a regular hour. You guys will learn a lot. And I can do that. That's a possibility. Any other suggestions? Now I cannot open it for the day. It's way too long. You know, the exam is 1 hour 15. I cannot open the whole day. This is impossible. Okay, so that's going to be the time. I think that's will be within your hour. So
Is there a chance it can be until 6? So if somebody start later, they can, finish at 6.
no more bargaining. Done.
Perfect. Thank you.
No more bargaining. Okay, so I will write this up today. Okay, so it's gonna be open at 1:30 p.m. I won't be with you at 1:30 because I have another class, but I will join you at 2 o'clock. It will close at 6 p.m. and the review, I mean, of course, it will be last year's exam or the year before, I forgot, with some extra stuff. I will go over the review with you by myself, and I will put the recorded lectures on Blackboard. This way, it will be fair. Are we set now? Any questions? Okay. All right. Very good. Okay, so I'll see you all guys on, what's the day today? On Wednesday. All right. Bye-bye, guys.